Everything begins with gambling, or at least the important modern history begins in 1654. And there was a well-known gambler in Paris named Chevalier de Méré, and he was perplexed by a seemingly inconsistent result in some of the popular games of chance that were played at the time. His particular question that he was dealing with was a game of betting on rolls of dice, and his question was, why, if it is profitable to wager that a 6 will appear within 4 rolls of 1 die, then why is it not profitable to wager that double 6s will appear within 24 rolls of 2 dice? De Méré took his question to his friend Blaise Pascal. Pascal began a very now famous chain of correspondence with another mathematician of the time, which is Pierre de Fermat. What resulted was a chain of correspondence extending for some years, for a foundation of the theory of probability resulted from that correspondence. Firstly, probability. A die has 6 sides, and if you roll 1 die, then there are 6 possible outcomes. Any one of the 6 numbers could come up. The chance of a 5 coming up, for instance, is 1 out of 6, because there's 6 possible outcomes, all equally likely. The probability of any event can be limited to the or can be expressed as the limit of the number of successes or successful outcomes over the number of trials. The second very big idea that's very relevant to gambling problems is the idea of mathematical expectation. Now, this idea was first attributed to the Dutch mathematician Christiaan Huygens, who is pictured there on the right, a weighted average of a random variable. And that equation at the bottom expresses the expectation of a random variable x is simply various values that x can assume each times its probability of occurring. So p sub 1 times x sub 1, p sub 2 times x sub 2, etc., sum together, and that would be a kind of weighted average outcome. If we look at the probability for, let's say, the return on a particular bet, there's a certain probability of a profit, so p times the profit, plus 1 minus p, which would be the opposite probability, or the complementary probability of a loss, and that would equal your expectation. Another property of expectation, which is very, very important for the gambler, is that expectation is additive. When you make a series of bets, each one of those will have a specific expectation. Your overall expectation, that is your overall average or mean result for a series of gambles or a series of plays at a particular game, is going to be simply the sum of the individual expectations of the bets you made. And so that leads to a rule number 1, as I'll call it, which is that the only way to achieve a long-term expected profit in gambling is to make a series of bets that have a net positive expectation. The last of the 3 big concepts I wanted to talk about is the law of large numbers. Gambling typically involves playing a series of repeated trials of a particular game. Independent trials, or repeated repetitions of an experiment, had been studied quite carefully by Bernoulli, Jacob Bernoulli, that is, of one of the Bernoulli brothers. Outcomes of repeated trials are often called Bernoulli trials in honor of Jacob Bernoulli. And down below we see the famous formula, which is the binomial distribution, and that is a formula which tells us the probability of particular numbers of successes in a given string of trials. As the number of trials increases, the expected ratio of successes to trials converges stochastically to the expected result. But what's more important here, and what's kind of more interesting as a phenomenon, is that the spread, or the possible variation in your result, is given by the blue lines first, is the 1 standard deviation spread, and the pink dotted line on the outside is the 2 standard deviation result. So basically, this chart describes what could happen to you in 100 trials of a very even coin flipping game with a narrow advantage towards the player. Your mean result is to be slightly ahead of even, so you would have made a little bit of money. But your actual result could very easily be anywhere within those different ranges. So you could be up or down. We're seeing 10 or 20 units, plus or minus, are quite realistic possibilities for where you could be after that period of time. This is what people typically face. Now, if you're in a casino, it would be very much like this, except that your expectation would be a little bit negative. Instead of having an expected positive result after an hour's play or after 100 trials, you'd actually have a negative expected result. So this would be sort of a a rotation of this graph around the x-axis with your probability of losing. But it would basically say that you could walk into a casino, and even if you had a negative or a negative expected result, in 1 hour's play or 100 trials, you could be anywhere. You could be winning a lot, you could be losing a lot. Now, what I've shown here is now the medium run. That was the short run, 100 trials. Now I've showing the medium run of the same game. So this is basically the same probabilities operating, except that this time I've run it out to 10,000 trials. So now what you see has happened here is that the expectation has grown much larger. We now see that we're have an expected positive return of about 100 units. And this has shifted where the standard deviation lines fall as well. Now we see that most of your probable return is very much above the x-axis. So you're heading to where you'd have to be at least one standard deviation below expectation. That is where the blue dashed line crosses the x-axis over around the 10,000 mark. So 2/3 or most of the time you'd be winning in this particular game, or I should say more like 5/6 of the time. So there'd only be results more than one standard deviation below chance would result in you being a net loser. So you're doing pretty good at this point. And let's go to an even longer run. This is the sort of the long run. Now this is maybe 100,000 plays at a particular game. And what you're seeing is that your expectation, the thick black line, has gone up considerably. You're now expected to be 1,000 units ahead. And the two standard deviation line shows that even if you've had an extremely bad run of luck, that is, you're doing much worse than expectation, you're still bound to be ahead, basically. So you're more or less guaranteed to be winning at this point. So this is the law of large numbers sort of applied to gambling in action. And basically what it's saying here is a sort of a corollary to the law of large numbers, that in a gambling game, your real result will eventually come very close to your expected result, or it'll become, the percentage-wise will become expected. So if you're playing an advantageous game with a positive edge for the player, you're definitely going to win eventually. But I had actually done these particular charts up for a talk about a winning gambling system. The truth of the matter is that for a typical gambler in a casino, it's just the opposite. All of these charts would be just the reverse. If you went in and played for an hour, you could be winning or could be losing. You'd have a small negative expected result. If you played for 100 hours, which would be roughly 10,000 trials of, say, blackjack over in Macau or something like this, you'd be almost certainly losing, but there'd be some chance, again, this graph would be reversed, there'd be about a 1 in 6 chance, that is greater than one standard deviation chance, that you might be ahead. But if you went to Macau and you played for 100,000 trials, which might be something like 1,000 hours of play, which a heavy gambler could do in a year, you'll certainly be behind, basically. There's almost no chance that you'll be ahead. So that's a warning to people who play games with negative expectations. Now I'd like to go on to something a little bit more interesting after those theoretical preliminaries, and that's the modern contributions of mathematicians to some unsolved gambling problems. The first one I'll talk about is an analytic result that was made by a gentleman named J.L. Kelly. And what he solved was the problem was, what fraction of his capital should a gambler risk on each play? What Kelly did was to define something called it's called the Kelly criterion sometimes, is he defined the exponential rate of growth of a gambler's capital, G, as being the limit of this x of n, which is final capital versus his starting capital, as a game is played on, and n being the number of trials. Now, the last one I wanted to talk about, though, and this is the one that's nearest and dearest to my heart, is horse racing. In racing, the challenge that you're faced with is trying to estimate each horse's probability of winning, dealing with real individual horses and modeling real-world phenomenon. So it's a departure from pure mathematics. Now, we could view the expected performance of a horse as being the result of a number of different variables or factors related to the horse's past performance or the condition of the race. That all can be expressed by the equation at the bottom, which is that the expected performance V of a horse is equal to a weighted sum of different different variables. An actual horse performance in a race, even though its expected performance might be a deterministic thing, you know, the sum of a number of different predictor variables, we all know from common sense that random things can happen in a horse race, or there might be unknown variables that are affecting the horse's performance. So we could say that an actual performance in an individual given race for a horse might be this deterministic component V plus some random error epsilon. So that's the expected performance of one horse. This would be a look at what an entire race of horses might look like. We might have, let's say, 10 horses in a race, or I think we've got 8 in this particular example. And what we see are a number of different overlapping normal distributions showing different potential running times for different horses. Now, I've intentionally made these so that each horse doesn't have an identically, an equally wide distribution. Some horses might be more consistent and have a sort of a narrower distribution of possible running times. Others might be more uncertain in their performance and have a wider standard deviation. This sort of mess right here is a number of overlapping predicted running times is what you really have in horse racing. And this leads to something called the probit model of horse racing. And the chance of a particular one of these 8 horses winning is sort of the chance that his performance will be the leftmost of all of these overlapping distributions. And that's expressed by the equation on the bottom. If we assume that that is the model of a particular race, then you can create a likelihood function which you can associate with a past series of race. And this was basically the likelihood of the observed winners in a series of, let's say, a past 10,000 races is going to be this product of the winning probabilities assigned to the horse that actually won in each of those particular races. I've included this graph just because I'm proud of it. This is the actual record of betting using the aforementioned horse racing system, or a methodology very similar to that. And this is a consecutive series of about 6,000 races, which was about 11 years of Hong Kong racing. And the graph is of a sort of an accumulated net profit that we experienced betting on this particular system. And in fact, to those of you who are mathematicians, which I assume is most everyone, the y-axis on this graph is actually a logarithmic scale, because the actual profit chart from using this system was, you know, very much very, very steep. So to make it fit on a particular page, we had to use a logarithmic graph. So it was, in the past, certainly it was true in the 1700s or the 1600s when all of this started. These days, it seems that rather than being the inspiration for innovations in mathematics, gamblers these days are more or less the beneficiaries. It's other factors that are driving the development of mathematics now, but keen gamblers are making use of the fruits of mathematics that was oftentimes developed for other areas of endeavor, and applying these same mathematical techniques back to gambling, and oftentimes to great profit. And there's a few references. Thank you.